Okay, questions?
I just have a general question about our restrictions. Like, we didn't feel, I feel like a lot of detail about
On which ones?
just RNS, like how to determine what's R versus S kind of thing.
Okay. So that whole process. That whole process?
Yeah.
Okay. We can start with that.
I don't know if this like relates to that closely. So I watched like both the videos on Canvas, and it talks about Fischer projections in the book, but it doesn't in the videos. Are those related to like how
The Fischer projections are another way of aligning the molecules,
okay.
and the Fischer projections actually would come in the next video that I would post. But the goal that where this all fits in is that first of all we need to be able to use the Coningle pre-log sequence rules, and those are left over from determining E and Z, and then are also used for R and S. So in terms of the sequence rules, they're used for both of these cases. They're used to judge priorities of groups. In the EZ case, just to kind of clean up the rest of chapter 5 and beginning of chapter 6, what we do is when we have our three non-alkyl groups attached to the double bond, and in this case 4, we have to use the sequence rules to judge priorities of the groups, but, and this is what might get a little confusing, with E and Z, I'm just going to determine the priorities of those two, which one's high or low. Then I'm going to go to these two and I'm going to say which one's high or low. And then if the two high priority groups are basically cis, that's Z. If they're trans, that's E. And so that's how we would use the sequence rules to determine priorities to give us E or Z. When we go to RRS, we're going to take all 4 groups and judge the priorities from 1, 2, 3, and 4. Okay. And what I don't want to confuse, and I'm going to invite confusion by saying this, is that we only do 2 at a time here. So I'm only going to do these 2 and then these 2. I'm going to do these 2 high priority, these 2 high priority. I'm not doing all 4. I'm just doing them 2 at a time in E and Z to create a cis-trans-like system. Okay. So my question to you then would be, E, and we did this in class, but I know we did it back then, and you're like, it wasn't going to be on the exam, so I'll pay attention when it's time. It's time. E and Toggen across is the equivalent of trans. Z, German for zusammen, together, literal translation from my 1 semester of German, 2nd semester senior year, thinking I needed a somewhat working knowledge of German when I went to graduate school, which they promptly got rid of that requirement. Cis. So, give you a minute. Is this cis or trans? Well, the answer is really easy. It's not. It's E or Z. So is this E or is it C? So take a minute and go through, and this will reinforce the Condigal prelog sequence rules, which is step number 1 to get us to R and S. And then if you have your Plicker card, we'll go ahead and I'll ask you E or C. Oh, hold on. I'm not ready. But apparently you are. Does everybody have an answer of E or Z? Okay, A, E, B, Z, C, don't know, question, have a question. Okay, ready? Okay. We have 29 E's, 6 Z's, and 2 I don't knows. Okay. So CH2I, CH2, CH3, which one has the higher priority? CH2 with the I. Carbon versus carbon tie. What's attached to that carbon? 2 H's and an I. What's attached to this carbon? 2 H's and C. Atom with the highest priority in the collection, I, wins. Over here, carbon versus carbon. What's attached to this carbon? 2 H's and a C. What's attached to this carbon? An H and 2 O's. That would be the equivalent structure of the aldehyde. And I think we did that last week, the equivalent structures. So in this case, which one wins? CH2, CH3, or aldehyde? Aldehyde wins. My 2 high priority groups are, in essence, trans, so that is E. Okay. So that is the E geometry. Right. So the first step in R&S is applying the Condigal prelog sequence rules, but now I'm going to do it to all 4 groups that are attached to the carbon, which is then called a chiral carbon. Okay. So here is a problem. Here are 2 problems from the book that somebody asked about on Piazza. So, and they were totally anonymous. So I have no idea whether it was this class or the previous class. And if you have the same question, remember, you can endorse it, which means then more than one person has that question. So let's look at number 1 here. So what I need to do with this is I need to determine for the 4 groups, I now need to rank them number 1 all the way to number 4 using the Cahn-Ingold-Prelong sequence rules. That's step 1. Okay? So, anybody want to offer for carbon number 1 here a group and a number?
The hydrogen and 4.
Hydrogen is number 4. That is always a good one to offer because hydrogen is always going to be the number 4 group. When it's present, it's number 4. There's nothing lower than hydrogen. A hydrogen with a mass of 2, called deuterium. Well, it's atomic number first, then mass. So actually, deuterium beats hydrogen. So there's nothing lower than hydrogen. It's always number 4. Okay. Anybody want to offer any other numbers? What I should do is give you a minute, and then you can tell me, and that's exactly what I will do. Number these from number 1 to number 3 now. Again, this is our first step. And don't make the mistake I made this morning of forgetting about this CH2 that is there. Because when I looked at this quickly this morning, I thought the oxygen was directly attached to the chiral center. It is not. Okay? So, and if you have your number, you could, well, just hold on to it for the moment. Does everybody have their groups numbered 1, 2, 3, 4? Okay, let me ask. I will ask, and you can hold up your card. So group number 1 is A, B is 2, and group C. So let's go around. Carboxylic acid. What ranking is carboxylic acid? Is it number 1, number 2, or number 3? The carboxylic acid that is on the top. All right, we have 28 number 1s. Okay, how about the CH2OH? What's it? Number 1, number 2, or number 3? I've got 30 number 2s. I guess that's going to leave the CH3 as number 3. Okay. So majority is right in each case. Carbon versus carbon versus carbon, tie. What's attached to this carbon? 3 H's. What's attached to that carbon? 2 H's and an oxygen. What's attached to this carbon of the carboxylic acid? 3 O's. So definitely CH3 is number 3. If I'm looking at 2 H's and an O versus 3 O's, 1 O cancels in both cases, which means it's O versus an H. O wins. So it is number 1, number 2, number 3, and number 4. Okay? So that's step number 1 of R&S. Okay, so let's see. I should know this because it did the, okay. So it goes 1, then 4, 3, and 2. So once you get the numbers assigned, now it's just simply a question of manipulating the numbers. You don't have to worry about the structures anymore, as long as you've got the numbering scheme. And these are the rules for R&S. Again, they're IUPAC rules. And what they say is the next step is to put the 4th priority group away from you. Point it away from you. Now, in the old terminology, like when I learned organic chemistry, we had what was called the steering wheel model. The steering wheel model would have the steering wheel and a long shaft. Well, that's the way cars were at the time. You had a steering wheel, you had a shaft, and then it went into the dashboard. Today's cars there's no shaft. There's not even keys in some cases. I still have a key. So the key is like where my shaft would be. But then, and nowadays you don't even have a steering wheel that looks like that. But the idea is we point number 4 away from us, so then I'm looking at group 1, 2, and 3. And group 1, 2, and 3 either is clockwise, which is R, or it is counterclockwise, where it would be 1, 2, and 3. Counterclockwise would then be S. Right? If going from number 1 to number 2 to number 3, when 4 is away from you, clockwise R, counterclockwise S. Okay. But we have to put the 4th priority group away from us. Now, what that means is that the 4th priority group has to go on a dashed line, on a dashed wedge. Okay. So in this case, I have 3 ways to orient this molecule with number 4 on a dashed wedge. The first is I can come down with my hand, and that's what that represents, is a hand, grabbing number 1, and if I grab number 1, then I can rotate the other ones, the other 3 groups. So I could rotate 4 into 2, 2 into 3, and 3 into 4. One will remain in its same place because I grabbed it. So I'm going to grab my model and I'm going to rotate it. So if I do that, then, and it's always critical that if I rewrite the structure, I rewrite it in exactly the same orientation. Same direction, same bold, same dashed. So in this case, 1 stays the same, 4 moves into 2, 2 moves into 3, and 3 moves into 4. So all I did was rotate that molecule. That's all I did. Small molecule all I did was, let's say, grab the top and rotate it like that. Okay. That's all I did. So 4 is now away from me. That's the goal. Get 4 away from you. Now going from 1 to 2 to 3, is it clockwise or counterclockwise? But there's another atom I can grab. Now, I can grab 4, or I can grab 1. I'm not going to grab 4 because 4's got to go to the back, and 2 is in the back, so I can't grab 2. I could grab 3. And if I grab 3, I can rotate 1. I can rotate 4 into 2, 2 into 1, and 1 into 4. So in other words, I'm grabbing it, now I'm rotating it that way. Okay. So if I did that, I would end up with 4, 3 didn't move, 4 into 2, 2 into 1, 1 into 4. So now again, I've accomplished my goal of putting 4 behind me. Going from 1 to 2 to 3 is now in that direction. Up here, going from 1 to 2 to 3 is in that direction. And that direction is clockwise, which hopefully I get the same answer the same way. So now I've got R. So that molecule would have been the R configuration. So if you have a molecule in a tetrahedron, and a Fischer projection is just another orientation of a tetrahedron, is all. If you can get it into the tetrahedron, you're only manipulating numbers. That's all you're doing.
Aren't you passing by potential number 4 when you look through that line, which is clockwise?
Well,
Aren't you going from
I'm going from number 1 to number 2 to number 3. I'm ignoring 4. Because in my steering wheel model over here, 4 is pointing away from me. So once 4 is pointing away from me, I ignore it. I'm only concerned with 1 and 2 and 3. Like this steering wheel. So going from 1 to 2 to 3 here is still clockwise. 4 is away from me. And say, this is a little bit different perspective, because I brought my bold wedge over a little bit more. This bold wedge should probably be more like that. So you ignore 4 after you've got it oriented away from you. So that's the way they came up with this system to always get the correct answer. So once 4 is away from you, ignore 4, go 1, 2, 3. Clockwise, counterclockwise. So if you get it into a tetrahedron, if you prefer, you can basically use a model and you can rotate it, or you can grab it and rotate it. You just grab not the dashed wedge, not the 4 group, any of the other 2, and then rotate 4 into the back. Does that make sense? Okay. So what I try and do with this is I try and give you different options. It's up to you to try and figure out, by doing problems, which one works the best for you. Okay. So the final answer is R. Now, also in the video, there is a chapter in the folder called Stereochemistry for Dummies, Volume 1, a chapter from that book. There, for a long time, wasn't a Volume 1. There is a Volume 2 now. There wasn't a Volume 2. Now there is one. The only place they documented group switching was in that book. Notice, that is not a standard organic textbook. Although the guy who wrote it, I think John Moore wrote it. He was a chemical education guru and was in charge of JChem for Journal of Chemical Education for a while. So he's not a slouch by any stretch of the imagination. But it is not a textbook. And I think the reason why group switching is not in textbooks is because it eliminates the need for spatial thinking. Okay? Now, whether that's a good thing or not is debatable. I think there are certain professions where spatial thinking is necessary. I think the dental exam has all these little polygons and stuff you're supposed to try and like move around and fit and stuff. So I'm assuming dentistry is a spatial reasoning profession, so that you don't grab the wrong tooth or whatever, or you try and fit the teeth. I don't know, but yeah, there are those. I've seen students have shown me that, so that's spatial. That requires spatial reasoning. But if you don't have the time for spatial reasoning, or you struggle with it, and I could let you use models on the exam, but then when you go and take like one of the AT tests, DAT, MCAT, something like that, no models. So you have to kind of learn how to do this in your head, although this is very good as you're learning. And if you don't have one of these, you can get little styrofoam balls. You could probably get a gummy and put 4 toothpicks in it. I have some of these if you want to borrow them. I didn't get all mine back from last year, but I do have some. Maybe you know somebody that still has it that you could borrow it from them. But a tetrahedron is helpful in terms of the model, but what if you don't, is there another way to do it beyond spatial thinking? And there is. I don't know I don't remember where exactly I picked this up. It's not my invention, like I said, it was documented in that book. That's why I included the chapter, that's the only place it's been fully documented, and I didn't have the time to write that. So group switching. In group switching, what you are allowed to do is you are allowed to switch 2 groups, switch, interchange, whatever you want to call it, any 2 groups, any even number of times. And if you do that, the configuration at the beginning will end up as the same as the configuration at the end. So right now, I know that's R, but if I didn't know that's R, I could say, you know what, I'm going to switch 2 groups on this molecule, my goal being put number 4 on a dashed wedge. 2 and 4. That is one switch. If I stop here and determine R and S, I will get the wrong answer. Because when you switch any 2 groups an odd number of times, R becomes S and S becomes R. So in other words, the configuration switches. So if your mind works that way, you make one switch, say, oh, that's S, and then write down R. Okay? If that's your system, I'm not going to mess with it. On the other hand, if you don't operate on the everything is the opposite system, then you can say, okay, I did one switch, now let's switch 2 other groups. And then I will end up with the same configuration I started with. What 2 groups do I switch? Well, I'm not switching 4. Although I could, I'd end up in the same place. So I can switch 1 and 2, 2 and 3, 1 and 3. Typically what you'll see me do is switch 4 and 2 and 1 and 3 in this case. Because 4, I want where 2 is. But I don't have to do that. I could switch 1 and 2 and say, okay, I've got 1, 2, 3, and 4. 4's behind me. You cannot determine R and S unless 4's behind you. I mean, you can, but you got a 50-50 shot of getting it wrong. The rule says 4 has to be behind you. Going from 1 to 2 to 3 better be R than it is. So if you switch any two groups, the purpose again, putting number 4 behind, if you switch any two groups an even number of times, you will get the same configuration at the end that you got at the beginning. Okay? So this is non-spatial thinking rotation. It is rotation without spatially thinking, if that's possible. Okay. So that's what the group switching technique is. Again, it's probably heresy with all of the true organic chemists who are like, you can't do that unless you spatially think. Sue me. Right. So that's another way of doing this. And I'm presenting you with different options here. Sometimes it's easier to group switch. And remember, all we're after is numbers here. Once you get the numbers assigned, it's a numbers game. The groups kind of disappear into the past. But you got to get the numbers correct to begin with. Well, actually, you don't. If you get the numbers wrong and then you get this wrong, then you might get the answer right. The thing about R and S is it's a 50-50 proposition. So when you do your problems, if you get them all right, great. If you get them all wrong, maybe you want to keep doing what you're doing and just write down the opposite answer. I mean, it would work. The biggest thing is if you get them 50-50. If you get them like 50% of the time, you're probably doing something systematic that's causing you to get them right only half the time. And if that's the case, if you find yourself doing that, come in. I'll have you do a couple problems and I'll see if I can pick up where you're being consistent or inconsistent in terms of doing that. But that's why you have to do problems, because the more problems you do, the more you'll become comfortable with this. And even to the point of looking at groups and going, oh, that's 1, 2, 3, 4. Very quickly. Okay. But that's how we do R and S. 1 through 4, orient 4 in the back, clockwise or counterclockwise, 1, 2, and 3. Forget about 4. And that'll get you your R and S. Okay. So here's one. Number 2. So try number 2 and tell me if it's R or S. And then when you have, your answer is going to be either A is R, and B is S. A is R, and B is S. Okay, we have 20 R's and 16 S's and 1, 3. Now that's close enough for a 50-50. So what we do with when you have a 50-50 answer is we give you a minute to discuss with a neighbor, and then we revote. So discuss with a neighbor, and then we'll revote.
But I started off didn't see it wrong because I forgot that there's a C here. So I think that's
Okay, we're ready to revote. So revote. After discussing it, what do you think it is? So we'll revote and see what we get. Okay, we moved a little bit. We're now 25 R's and 12 S's. So we move towards the R answer. So then the question is, did we go in the right direction? So question number 1, okay, let's rank the groups. Hydrogen is definitely number 4. Methyl group, 3. O with the CH3, 1. So this might be the difference in why we're getting 2 different answers. So, okay, so let's go back to basics. Hydrogen versus carbon versus carbon versus oxygen. Lowest priority group, hydrogen. Oxygen versus carbon, who wins? Oxygen. So the oxygen becomes number 1. Carbon, CH2 with the carboxylic acid versus CH3. Basically, a C with anything other than a 3 H's is going to be a CH3. So this is going to be number 2, and this is going to be number 3. So 4, 3, 2, and 1. In theory then, since this molecule is in exactly the same orientation as the one on the left, and the numbers are exactly the same, it should be R. And so we've got a 1, a 2, a 3, and a 4. If I do my group switching, I'm going to switch 2 and 4. And this time I'll switch 1 and 3 just to be different. 1 going to 2, going to 3 now since 4 is in the back. Going from 1 to 2 to 3 is clockwise, so that is the R configuration. Any questions? So any one of these steps, any misstep you take, could get you the wrong answer. There is a saying, right? 2 wrongs don't make a right. Well, here it could. If you got the wrong order, but then you messed up the 1, 2, 3, 4, you could get the right answer. Or we could flip a coin for R and S and have a 50-50 chance of getting a correct answer. All of which are probably equally successful, except going through the problem is the best way to get the correct answer instead of guessing. So that's the steps that we're going to use for this. Does that make sense to everybody? But now what we want to do is now we want to twist, and we want to start with different kinds of molecules. And before I do that, let me go back here to where I was doing hands here. I'm grabbing and rotating. Now, when I move 2 into 3, 3 into 4, and 4 into 2, did anybody have a sense of deja vu? What was your sense of deja vu? Exactly. This is exactly what we did with the Newman projection from a different perspective. The different perspective being, I'm here. So if I rotate the molecule up, when I'm rotating like this, what am I doing? I'm rotating the front carbon on a Newman projection. Okay. So it is what we did before from a different perspective. Now, there are other orientations here that we have to work with. The other molecule that there's different things. First of all, well, I'll just show you the possibilities. We'll go through these, including on Friday. So let's say we did this. So let's say I gave you this molecule. This molecule cannot be named cis or trans. Why? Because there's 3 non-hydrogen groups on the ring. If there's 2, I can tell you cis or trans. But when there's 3, how do I have to name this? Well, I have to go through my naming and figure out which carbon's 1, which carbon's 2, which carbon's 3 and 4. And then the only way to name this exact molecule is to say, well, this is the 1R, 2S, 3 or 4. It's 1, 2, 3, 4. The 1R, 2S, 4S molecule. So I'm going to have to apply the exact configurations of those chiral carbons. Configuration means exact 3-dimensional structure. And that's what the R and the S is doing. Okay. So I'm going to need to do that for a cyclohexane. I'm going to need to do it for a molecule that's oriented like this. So if I take my Newman, or if I take my little molecule here, and I orient it like this, okay, this is small. The 2 bonds are coming towards you are horizontal. The 2 bonds that are pointing away from you are vertical. That is what is called a Fischer projection. And a Fischer projection is abbreviated like this. Okay. And that was in the reading, but I'm now going into my next series of topics. So the Fischer projection looks like this. This corresponds to that. I remember that as a bow tie structure. That's how I remember the orientation. I do know where I got that. I got that from an Apple IIe tutorial program. For those of you not alive when the Apple IIe came out, it's the one with the green screen. No color, just green. Probably worth $50 if you had one today. That's probably worth a little bit more than that. But that's how they did the green. That's how they enforced the bow tie structure. So the bold wedges are horizontal, the dashed wedges are vertical. Fischer projections are actually pretty easy with group switching, because all you have to do is put number 4 on a dashed wedge. Which dashed wedge? Doesn't matter. It's just got to go on a dashed wedge. So group switching works really well for Fischer projections. If I put two carbons together in a Fischer projection, I get this, where I would have the bold wedges horizontal and again the dashed vertical. So this has 2 chiral centers in it. And we're going to have to be able to look at top and bottom. Are they R or are they S? So Fischer projections can be 1 carbon or they can be multiple carbons. Fischer, because I just saw this on the elevator the other day in this day in chemistry, because I always have a hard time, does it have a C or doesn't it? It does have a C. But reading his little biography, Fischer developed the Fischer projection, but he did all of his research on sugars. So if you in biology class have seen something like this, could be in genetics too, there's usually it's 6 carbon chain. I might have left one out, but if you see something like that looks like that, that is a sugar, and that is a Fischer projection of a sugar. So all the horizontal lines are bold, and there are 1, 2, 3 chiral centers in that sugar. And they are usually well defined so that each one has a specific configuration, R or S. And if that sugar does not have that exact configuration, that sugar will not do whatever it needs to do in metabolism. Okay. So that is just a Fischer projection. We'll have to figure out how to do R's and S's on those. And then finally, my Fischer projection here is basically has the molecule oriented like this with 2 chiral centers. Well, what happens when I take those 2 chiral centers and I do this with it? What do I make? I make a Newman projection. So if we're given a Newman projection with a front chiral carbon and a back chiral carbon, can we tell whether the front carbon is R or S? And can we tell if the back carbon is R or S? Okay. So once we've got the system down of 1 to 4, orient 4 in the back, determine R and S, we now need to do it with just more than tetrahedron. We need to do it with cyclohexanes, we need to do it with Fischers, we need to do it with Newmans. Okay. And so that's what we're going to do on Friday. as well as, if we have time, talk a little bit about, well, the first video in today's folder, the first video I got into just the overall idea about being chiral and what impact that has. My intention is Friday we'll do R's and S's on these. And then on Monday, I have sort of a little lecture on an enantiomeric excess, percentage R, percentage S, percentage D, percentage L, with some practical examples from some research stuff that I've done. So my intention was on Monday to give a lecture on that, which will then talk about the enantiomeric excess. But if you have questions, I did answer one of those last night. Somebody asked if I would redo that or talk about what the book was because it was kind of confusing. I will probably do that on Monday. So I'm going to reconfigure the reading assignments a little bit. But on Friday, our intention is to be able to become proficient at R and S for these molecules. And then what we will do is we'll talk a little bit about enantiomers and diastereomers also on Friday as well. Okay, so those are the topics we'll do. I'll send out an email when I get all of that reconfigured. But if you need to, there's problems on R and S, there's problems on Conningle pre-log sequence rules, there's E and Z problems, and then there's some back probably in Chapter 5 as well. Okay? If you have any questions, post them to Piazza, send them to me. Otherwise, that's what we'll do on Friday.